Exercise 1108 is extension content about inverse trigonometric functions. Now remember, to find an inverse function, you switch x and y and you make y the subject. So if we have the function y equals sine x, we switch the x and the y, x equals sine y. And then, so we've actually learned the inverse functions before. You just take sine inverse of each side. So sine inverse of x equals y. Let's just turn it around. So sine inverse of x that we've talked about, that's the inverse trigonometric function for sine. And just like if you had y equals cos x, then the inverse function is y equals cos inverse of x, which we've seen before. Now I might just change that to function notation. Okay, now also if you're Googling these functions, sine inverse of x is also called arc sine. So for Google, you might need to look at arc sine, or if you're entering it in Desmos, you can type in arc sine for that function. So inverse, so -1 there. Remember that power of -1, that doesn't mean reciprocal, it does mean inverse. If you've got 1 over x, then the multiplicative inverse of that is x, right? So this is x to the -1. In this case, the reciprocal is the inverse, but in some cases that's not the case. The inverse here is not the reciprocal, that's the multiplicative inverse. Now I've added tan there as well. So in terms of cos, that is also known as arc cos, and in terms of tan, that's also known as arc tan. So if you're Googling, that's what you might want to use, or Desmos. Okay, so graphically, you may remember that to find an inverse function, we have to limit our domain firstly, so it's either monotonic increasing or monotonic decreasing. So remember, if it's monotonic increasing, it never decreases. So I've cut off these bits that decrease. It also, because it's always increasing. Now here it's decreasing as well, so I've cut off that as well. So I've limited my domain from -π/2 to π/2 so that the function is monotonic increasing. So my limited domain is that x is from -π/2 up to π/2. And I've graphed in black there the sine curve, so that there is sine x. Now to find my inverse function, I do reflect that through the line y equals x. So this point here that's at 1 π/2 1 is going to end up here at 1 π/2. So π/2 is just a little bit over 1.5, so there's one that's a little bit over 1.5. So this point's going to end up about there. That point is going to reflect through there over to there. The sine curve down here is almost exactly the same as y equals x, so that's going to be the case on our inverse function as well. So it's just going to go like that. And the same thing here, this point will reflect over here to -1 π/2, and that's going to look like that. Okay, so I will draw that again separately. So I really just wanted to draw this on another scale to really emphasize the shape, because it's kind of like the sine curve is going that way, up and down the page, instead of across the page. So you can see our domain here and our range have switched from what they were before. So our domain is from -1 to 1, and our range is from -π/2 up to π/2. So that's the shape, and I'll show you that on Desmos too. Here I am in Desmos, and I've drawn the curve y equals sine x on that limited domain. So I'll just remove that limited domain for a second. You can see that sine curve there, but we've limited by cutting it here and here so that it's monotonic increasing all the way. I've also graphed the line y equals x, and you can see my scale is in terms of pi along here, but that'd be about 1.5, okay, just a little over 1.5. So 1 would be around here somewhere. Now I'm going to graph y equals arc sine x. And there it is. You can see it switched, but only on that limited domain. So in this case from -1 to 1 in terms of x, and vertically in terms of y from negative pi on 2 up to pi on 2. So even if I get rid of this limited domain on my original function, you can see the arcsine function is only defined on that very limited domain. So let's look at cos x, the cosine of x, and its inverse, arc cos or cos inverse. So I've got the cos curve and I want to limit the domain to being monotonic decreasing. So here it is here from 0 to pi. You can see I've gone 1, 2, 3, so there's pi at 3.14159, etc. Pi on 2 just a little over 1.5 here. So the domain is limited from 0 to pi. Now I'm going to reflect that through the line y equals x to find what the curve of cos inverse looks like. Now I do recommend actually drawing this yourself and pausing the video and having to go yourself before I do it with any of these. So here I go. So this point here will get reflected to there, okay, through the line y equals x. This point here will get reflected up in that direction. So instead of being pi negative 1, it's going to be up there at negative 1 pi. So it's going to be right there. This point here where we cross the axis at pi on 2 is going to cross the axis up there at pi on 2. So you can see those points now. And if we can connect them up like a general cosine curve, so just like here, how the gradient here is actually -1, this gradient up here is going to be similar. We're going to have this general shape. So going through there on a gradient of 1, coming down like that, and then going up that way like that. And at that point it would come back round if we didn't have to limit the domain, but we do. Otherwise it just wouldn't be a function. Now the domain and the range, in order to do those, I have just drawn it again just to really emphasize that shape a little bit on a scale that's not a 1-to-1 scale. It just makes it a little bit more obvious, but think of like a cosine curve going this way instead for that shape. So if it wasn't a function, if it was a relation, it would come back down again up there. So you can see the domain is -1 to 1, so I'll just put that up here. And the range goes from 0 up to pi. So again, they are flipped. So where cos was limited from 0 to pi, and the range of cos, as always, is from -1 to 1. Okay, on an inverse function, of course, those two things get switched. Sine x, but here with cos x. So I need to limit my domain. With this one, I'm going to limit it to where it's monotonic decreasing. So from x equals 0 to x equals pi. So there's my limited domain. And now reflecting it through the line y equals x, there's arc cos x. Okay, so let's do the same thing with tan x. So I've just limited the domain between the asymptotes from negative pi on 2 to pi on 2. And the range there is negative infinity to infinity. We can see that. Now, here's the line y equals x drawn on there. So we need to reflect through the line y equals x. Again, pause and try and do it yourself first. You can think of the asymptotes. It's almost like they rotate 90 degrees. Sometimes flipping through the line y equals x can appear like a rotation through 90 degrees, but that's only for odd functions. So this asymptote at pi on 2, which is about 1.5, will actually end up about here. Actually, my scale here, I've made that 1.5, so my 1 is slightly below 2/3 of the way along, so that pi on 2 is exactly up there. Now this point here, that's at pi on 4, 1, that's going to reflect to 1 pi on 4. So that's going to reflect, pi on 4 is there. Okay, halfway to pi on 2, so that's pi on 4. So this point here is going to reflect to there. And the same thing down here, where negative pi on 4 and negative 1, that's going to reflect to negative 1. So I went 3 squares for pi on 4. That's going to go there. So there's negative pi on 4. And down here at 6 squares is negative pi on 2. So this point is going to reflect to there. So let's have a go at drawing that. Again, the gradient here is pretty close to the gradient of y equals x, actually equal to. So that's going to look like that. Actually, I'm much drawing that as asymptote. There they are at pi and 2 and negative pi and 2. So our curve is going to head towards that asymptote that way. And down at this end, it's going to go, oops, through this point, sorry, like that. I have drawn that again neatly down here. I'll mark those points pi on 4 as well. They're quite useful points, negative pi on 4. So you can see here domain and range. Domain is now infinite, and the range is now from negative pi and 2 to pi and 2. Okay, I've written those there. The exact flip, of course, of what they were up there. So there's our arctan or tan inverse curve. Tan inverse. You can write it like that, call it tan inverse, call it arctan. We do generally tend to call it tan inverse, but I think it's really since the internet and more international things and being able to type it online as well, that slowly arctan is becoming more and more common in Australia. Different countries do it in different ways. So just looking at tan inverse, so I've graphed tan, I've graphed y equals x. Now I'm going to limit my domain again, so it's monotonic increasing. Now I need to limit it so there's only one of them. So if we limit it from negative pi and 2 to pi and 2, then we've just got that little section there. So then we reflect that through y equals x to see the tan inverse function, and there it is. So you can see with that one, our domain is actually infinite, but our range is limited to between where those asymptotes are at negative pi on 2 and pi on 2. Okay, so in this example, we're asked to graph y equals 3 cos inverse of 2x. Now, I am going to explain this a whole lot better in Year 12, in Chapter 4 of the Year 12 book. So just bear with me a bit here. That 2x is going to be a little bit confusing, but I will do a Desmos as well. So here's just the original function of cos inverse x. So remember, domain is -1 to 1, and it goes up as far as pi in the range, so 0 to pi in the range. So 3 is what we call a vertical dilation. Just like it changes the amplitude with cos x, it stretches it up. So it's a vertical dilation that stretches it by a factor of 3. So that changes the range. So down here where cos inverse has a range of 0 to pi, 3 cos inverse would have a range of 0 to 3 pi. That's going to get multiplied by 3. That bit's pretty easy. Now, the thing that is confusing is the 2. So 2 is a horizontal dilation. Now, a dilation can be something that is stretched, or it can be something that's shrunken. So it can go either direction. If the dilation is, depending on the number, if you're multiplying it by something or halving it, for example. Now, horizontal dilations work in the opposite way to vertical dilations. Where a vertical dilation of 3 stretches it, a horizontal dilation of 2 actually shrinks it. It actually halves it. So where this multiplied by 3, this one halves it. It's 1 over. The 2x has to fit between -1 and 1. Okay, I'll just come down here. So the 2x has to be between -1 and 1. So if I halve that, if I divide everything by 2, then my x, which is my domain is all about my x, not my 2x, is between half and -half. So my new domain is -half and half. Okay, it's a little bit confusing, I know. So we're just going to apply those transformations to the graph and graph it. So I'm just going to change my camera angle a little bit. So where I did start here and finish up at pi, I'm going to finish all the way up there at 3 pi. But I'm also going to shrink it this way. So it's going to be really tall and skinny. So there's my half. Instead of starting at 1 now, it's going to start here at half. Instead of reaching all the way to -1, it's going to reach to -half. Okay, so instead of going a range up to pi, it's going to go all the way up here to 3 pi. So there's a point, here's a point. This point right in the middle has stretched up as well by a factor of 3, so it was down here, as we can see up here at pi and 2. It was at pi and 2. If you times that by 3, it's up here at 3 pi and 2. So a very, very long, skinny curve. I'll do that in Desmos as well. Transformations in Desmos. So the K is a really obvious one. it stretches it up. Let me just change my view slightly. So you can see as I make k bigger, it stretches it up further. As I make k smaller, it stretches it down. If k goes negative, it flips through the x-axis. So that one's really obvious. I'll just set that back to 1. Now let's look at the a. So I've got cos inverse arc cos of ax. Now at the moment I've got a set. Let's just set it to 1 to begin with. There we go. So that's normal now. So right now we just have y equals cos inverse of x. So here we are here at 1, minus 1. This is pi up here. Okay, so 0 to pi. That's the normal one. Now, what I'm going to do is increase my a. I'm going to make my a bigger number, and we are going to see the dilation, the horizontal dilation, come in towards 0. So let's have a look at that. There you go. So it's coming closer and closer to the y-axis. It's shrinking it horizontally. Not stretching it out, actually shrinking it. The bigger the a is, the skinnier my curve is. Now, if I did go down and make it a fraction, it would stretch it out further. So let's make it a fraction, and it really stretches it out. So if a now is 0.36, is about a third. The width of this is about 3 times, it's not exactly a third, but close. It's about 3 times wider than what it was originally. So it is a bit counterintuitive that making the a bigger shrinks it and making the a smaller stretches it, but that is what happens horizontally. Vertically, it's much more intuitive. You increase it, it gets bigger. You decrease it, it gets smaller.